So in Kepler's third law lab, you've discovered that the cube of the semi-major axis is proportional to the square of the orbital period. All right, this is what Kepler came up with. That the farther out a planet is, the longer it takes. And the relationship between that distance and that time, all right, has a slightly complicated relationship. Newton, though, took that a little bit further, and instead of just putting it proportional, he also set it equal. And when you set it equal, you have to have some kind of conversion factor, which we put in as k, and as we saw, k is actually the mass of the central star, or the planet a moon is going around. So when we want to weigh an object, this is one way that we can do it if we see something going around it. And I'm going to do one quick demonstration on how to just run through a very basic problem, and then I'm going to give you a more complicated problem with some more conversions in it that is actually relevant to how we calculate a planet's mass. So here's just a random question. If you were to record that a star had a planet that went around it in 5.3 years at a distance of 2 AUs on average, we can actually measure how massive that star is. It's not actually its weight, all right, which is just the force of gravity on it, which we'll get into later, but how massive it is. All right. Notice how it doesn't have anything to do with how massive that planet is. That's an interesting relationship. But we're going to be using Kepler's third law, all right, that the mass of the central star or planet is proportional, or excuse me, is equal to the cube of the semi-major axis over the square of the period. Now, we got to pull some information out here. Again, A is the semi-major axis, which is basically the average distance a planet orbits around a star. All right, in this case, it's 2 AU. And the orbital period, P, all right, is 5.3 years. Now, we don't have to do any conversions on this. All we have to do is plug it into our equation, and lo and behold, we have a star that is 1.5 times more massive than our own star. We don't have to go there and do any weird calculations. All we need to see are objects going around it. Now, let's bring it back home to an actual situation. What if I want to measure the mass of Jupiter? All right. How can I do that? Well, let's go ahead and take a look. So this is the last of Kepler's Vcast. This is Kepler's third law, and it has to deal with the time it takes for planets or moons to go around the object they're orbiting and compare it to the distance that they're orbiting. In fact, what you should have found is Kepler's third law states that the square of the orbital period is proportional to the cube of the semi-major axis. Or you may have had that flip-flop, but the idea is that those two things are proportional. In part 4, what you did was actually continue on with where Newton took this. He did not set them proportional, but he actually put them equal to one another. And he did that by adding in the constant k. Now, you also went through in part 4 and figured out what k was, and you should have known that k is actually the mass of the object it's going around, measured in solar masses. So in other words, this is how you can tell how heavy an object is. All right, the technical term should be mass, or how massive it is, and I'm going to prove that to you by running through the simulation, and we're going to actually weigh Jupiter. All right. So what we have here is a simulation that we've zoomed in on Jupiter. And there are the 4 Galilean moons here that are in orbit around it. That's Ganymede. But we're going to be looking at Io. Io is in orbit around Jupiter. And if we want to weigh, or a better term, mass Jupiter, what we're going to need, if we're going to use Kepler's third law, is how long it takes to go around Jupiter. So its orbital period, which is a little more than a day. And we also need to know how far away it is. All right, the semi-major axis, which is basically just the average distance. And we can do both on this simulation. So let's go ahead and get started. So I've zoomed into Jupiter and Io. and I can use my separation tool here to actually measure that distance. So that distance from the center of Io to the center of Jupiter is 420,090.5 kilometers. Alright, so that's my semi-major axis. Since it's almost a perfect circle, we can just use the radii. So the next thing we need to do is determine the orbital period. How long does it take for Io to make one complete revolution around Jupiter? So let's make note of the time and the date. We've got 1:30 universal time, and it's March 16th. And we're going to fast forward through time here and allow it to come across Jupiter, and then we'll slow it back down. And that looks pretty close there. Alright, so it's taking until March 17th, 19 hours and 52 minutes in order to go one complete revolution around the Sun. And based on those numbers, which I'll walk you through the calculations, we're going to actually determine the mass of Jupiter. So we're going to be using Kepler's third law here to actually determine the mass of Jupiter. Technically, weighing is different, but for now, you guys don't know too much difference. We'll use that term. So we know here's Kepler's third law. We need to know the semi-major axis. Now, here's a catch. Our semi-major axis we measured was in kilometers, but it has to be measured in astronomical units, an AU. Now, just as a quick review, an astronomical unit is the average distance between the Earth and the Sun. All right? And that works out to be about 150 million kilometers. So if we want to convert that, and we have to, here's how you're going to do that. You're going to take your distances in kilometers, all right? And then you're going to multiply it by this ratio, okay? 1 AU is equal to 150 million kilometers. So what happens here? The kilometers cancel out. You take 420,090.5 kilometers and divide it by that 150 million, and you get 0.0028 AUs. All right, so that means it's very, very small distance in comparison to the distance between the Earth and the Sun. Now, what about the orbital period? Orbital period, we measured time in the hours and the days, but again, it needs to be measured in Earth years. All right, how long it takes for Earth to go around the Sun? Well, this only took a little over a day. In fact, one day, 18.37 hours. You're going to have to do some kind of conversions here, so this is where it becomes really important to take good notes for these examples. We need to convert one day, 18 hours, 18.37 hours into years. To do that, all right, it's going to be a little complicated, or it's going to look a little complicated, but let me walk you through it. That one day, we know that if we multiply it by our ratio here, our conversion factor, that 1 year is actually 365 days. That's going to take this into, or put it into years, because it's going to cancel out the days, leaving you with the years. And then if we add that 18.37 hours in there, again, we have to convert that into Earth years, and we know that there are 24 hours in a day, so the hours are gone. And then that puts that into days, and then you convert that into years. All right, 365 days per year. Hours cancel, days cancel, and you're left with how many, or what fraction of a year that is. And it all adds up to be a very small amount of time, of 0.00484 years. Give or take. There's a slight bit of rounding in there. All right. You will have to do some of these conversion factors, so it's important that you understand how they work. If you're not sure, please ask. All right, so when we plug that in, we get that Jupiter, the largest, most massive planet in our solar system, is a very small mass compared to our Sun. 9.37 times 10 to the negative fourth solar masses. All right. This is far less than 1% of the mass of the Sun. All right. And when you work this out, that gets to within 1% error. You could convert this into kilograms if you wanted to. I don't think we'll need to, but that is a very accurate measurement from some very basic measurements that you could do if you had a little bit of knowledge and a telescope at home.